Hello everyone, this is Mrs. Lindsay. Today we're going to do example 4 with our related rates notes, the lighthouse problem. But before we actually jump into this, let's read the note above here. Angles must be measured, that's a typo there, measured in radians when we use differentiation formulas. Those formulas were developed from measuring in radians. So again, radians here, whenever we're working with taking the derivatives. Okay, so let's jump into our problem here. A lighthouse is located on a tiny island 3 kilometers north of a point A on a straight shoreline. The lighthouse lamp rotates at 5 revolutions per minute. How fast is the illuminated spot on the shoreline moving along the shoreline when it is 6 kilometers from A? So again, let's identify what we have and what we know later, and we probably want to draw a picture here. So let's take a look here again. A lighthouse is located on a tiny island 3 kilometers north of a point A on a straight shoreline. So if I just literally have a point A, I'm going to go straight north 3 kilometers. That's not very straight, but that's straight north 3 kilometers till I get to my lighthouse. So I'm going to just abbreviate that LH. Okay. The lighthouse lamp rotates at 5 revolutions per minute. 5 revolutions per minute. Okay. How fast is the illuminated spot on the shoreline moving along the shoreline when it is 6 kilometers from A? So here, again, here is my shoreline. Just go ahead and draw that. Alright. And we have, again, some distance away where this light is shining out. Okay, obviously that's the lighthouse lamp is rotating 5 revolutions per minute, so that will change eventually. Okay, and again, since we know this is straight north, we do have a right angle here as well. Okay, alright, so let's take a look at what we have here. 5 revolutions per minute. So if we think about that, we have 5 revolutions per minute. Well, let's label what that is. Okay, so hopefully you're thinking about this is where that lamp is. And again, the light is rotating, so we're referring to our angle here. So this is really our rate of d theta over d time, dt. Okay, so how fast is the illuminated spot on the shoreline moving along the shoreline when it is 6 kilometers from A? Well, we got to think about this just a little bit. If I have theta here, hopefully you're remembering from the past, if I have in a right triangle the opposite side and the adjacent side, hopefully we're ringing a bell that that might be SOHCAHTOA tangent. So that would be x over 3. Okay? So this is all our given information, but we also have some information later because we want to know how fast is it illuminated on the shoreline when it is 6 kilometers. So that's later. So later on, we want to know when x is 6 kilometers. Okay? But before we can do anything with that, we have to take the derivative. So we have a couple things here when we're talking about our related rates, but we need to go back up here and think about it needs to be in terms of radians. Well, here we don't have our angle in terms of radians. So a little bit of review from geometry here, or factor labeling, if that rings a bell. Actually, this you probably did this in pre-calculus. We need to convert this. So when we have a revolution, one single revolution around the circle, so one revolution around the entire circle, in terms of degrees is 360, but in terms of radians, it's 2 pi. Okay, let me go ahead and do this. Later information. Okay, so 2 pi revolutions, 2 pi radians is 1 revolution, so that would cancel. So now we have in terms of radians, so I can go ahead and multiply across here. So 5 times 2 pi is going to give me 10 pi per minute, and now we have it in terms of radians. Okay. So, before again we plug anything in, let's see what we have here in terms of finding our derivative. So the derivative of tangent is secant squared theta d theta dt, again, implicit differentiation with respect to time. Now, recall, x over 3 can be written as 1/3 x. So the derivative of that would simply be a third. Again, find the derivative with respect to time, dx dt. So now we have taken our derivative, and let's see what we know. Well, we know d theta dt is 10 pi. So it's 10 pi here. We have a third. Dx dt, well, that's how fast it's actually moving, so that's the rate that we're looking for. But what are we going to do with this secant squared theta? Okay, well, hopefully you're thinking, let's go back to our right triangle here. This is the reciprocal. Let me go ahead and write down SOHCAHTOA here in case we need to refresh our memory. Secant squared is the reciprocal of cosine. So instead of adjacent over hypotenuse, we want hypotenuse over adjacent. Well, what is our hypotenuse? We clearly have our adjacent side of our angle here, which is going to be 3. We need to figure out what that hypotenuse is. Okay, so if we use our later information, which we now can do because we've taken the derivative, we know that's going to be 6. So we can do Pythagorean theorem, 3 squared plus 6 squared equals h squared. Do a little bit of arithmetic here, so we'll get 9 plus 36, which is 45. Square root both of those. So h is going to be square root of 45. We can reduce that, but as of right now, let's just go ahead and leave that, because if we now plug in our secant squared here, which is hypotenuse over adjacent, we'll have square root of 45 over 3. But that is squared. Should probably draw a line here. That's getting a little confusing. Now I can actually move this. I'll move that over just like that. Move it over just a little bit. Okay. Alright, now we're back in business here. So when we square this, square root of 45 squared is simply just 45. 3 squared is 9. Times 10 pi equals 1 over 3 dx dt. And we'll just simply keep going until we solve that for dx dt. So 45 over 9 times 10 pi equals a third. Why don't you go ahead and actually pull out your calculator at this point in time. I'm okay with a decimal at this. Pull out your calculator and calculate what that is. When you get that, push play to check your answer. Okay, 471.24. But again, how are we going to label this? Let's look back out of our problem here. So this is our distance over time, right? So dx dt, our distance is measured in kilometers, our time is in minutes. Okay, and this concludes problem number 4.